Hey guys, and welcome to our Unit 4 test retake video. So just like normal, at the end of this video, you'll be given the password to retake the Unit 4 test. This was a difficult test, I will say that, so I'm glad you're watching this, and good luck on the retake. Also, like normal, these questions that I'm going over are directly from the test. I sort the test based on question difficulty, and as a class, the questions I go over, they're taken directly from the test, and they were the most difficult questions on the test. And so hopefully paying close attention to these and how to do them, and the answers will help you on the retake. So starting off, we have which of the following measures thermal energy of an object? Now, this was a really tricky question. I actually don't like this question that much. It's asking you for a slight difference between basically the definitions of temperature and heat, because those were the answer choices. You had mass, temperature, heat, and volume. And by far, most people chose heat for this. It was between heat and temperature, and most people chose heat. Heat is not correct. It's temperature is a measure of the thermal energy of an object. Now, the difference between these words is very subtle, and so heat is the total thermal energy of an object. Heat is the thermal energy of an object. However, it's asking us for a measure of the thermal energy, and temperature is the measure of that thermal energy in an object. And so heat is actually all the energy of an object. Heat is all the energy, the molecular motion of an object, and temperature is a measure of the thermal energy. Okay, so we want temperature. Which of the following measures thermal energy of an object? Well, temperature is a measure of thermal energy. And that may help you if you remember temperature and thermal. You know, temperature is kind of a measure of heat. Like the hotter it gets, you can see it on your thermometer. So temperature is measuring how hot it is. All right, next. Which of the following is likely to be true about the delta H for this reaction? And then you're given only three choices. You're given delta H equals 0, delta H greater than 0, or delta H is less than 0. And the key part here, and I didn't, this is should be an arrow going here. It didn't copy, so just like a chemical reaction. C6H6 as a liquid, the key here is looking at the phases, is a liquid, and then it changes. C6H6 goes to a solid, so we're melting, right? And it always helps maybe to think of an ice cube, because we can all picture that, right? You have liquid water and it's going to solid, so it's going from liquid water to an ice cube. And so first we need to know, is that an exothermic or an endothermic reaction? It's freezing. Freezing, remember, is an exothermic reaction. And you can remember that because if we go the opposite way, if we go from solid to a liquid, melting, like holding an ice cube, a solid ice cube to water, your hand gets really cold, right? And so that if it gets really cold, that's endothermic. However, we're going the opposite way. We're going from liquid to solid, and so it's opposite. It's opposite of endothermic, which is exothermic. So going from a liquid to a solid of any substance is exothermic. Now, it's not asking for that, though. It's asking for what's the delta H, and so we need to remember exothermic has a delta H less than 0. It's negative. Negative delta H. And so it would be this one right here, right? Because we know it's exothermic, and the delta H, the change in enthalpy of an exothermic reaction, is negative. And that's what this one down here means, is delta H is less than 0, so it's negative, so it's exothermic. Okay, which of the following parameters is kept constant in a coffee cup calorimeter? And then the choices were temperature, volume, pressure, and kinetic energy. The big, lots of people selected temperature. The correct answer is pressure. And I think lots of people selected temperature because in our lab, if you remember the lab that we did for this, that's what you measured. You had that big calorimeter, and then you put the thermometer in it, and you took the initial reading, and then you stirred it up until and then the temperature went down, and you took a final reading. So just because, so that should tell you right there the temperature was not held constant, right? Remember in that experiment, the temperature started out at like 20 some, and then it went down to 0 degrees. So that temperature is definitely not held constant in a calorimeter. Pressure is what's supposed to be held constant in a calorimeter, not the temperature. And if it helps you to remember that, lad, think about how we measure the temperature and about how you saw that temperature dropping. You saw that temperature changing. So it definitely is not temperature that changes in a calorimeter. Okay, next one. How much heat do you need to raise the temperature of 150 grams of ice from 30 to 15 degrees? And this is actually, there should be negative signs here. Negative, that's why you're raising the temperature, right? Yeah, it's going from negative 30 to negative 15 degrees. And then you're given this this table right here with specific heats. Remember these right here, C equals specific heat. So these are specific heat of different substances. Now, once you should recognize it's asking you how much heat. So this sounds like a specific heat problem, right? And then so write down your specific heat equation. C equals Q divided by M delta T. And now let's see if we can solve for anything here. We have our temperature. Oh no, yeah, we do have our temperature change from negative 30 to negative 15. So it's the temperature change. Remember this little triangle, delta means change in temperature. And so the temperature changed by 15 degrees. M, we have M, there it is, 150 grams, right? That's a mass. M is the mass, 150 grams. And then we actually have C also, because we know it's ice. And we have our table here. I can go over and say, oh, look, it's ice. And then here's our C, 2.5. And so C right here equals 2.5. We'll write it here. C equals 2.05, sorry. And so now we have 3 out of the 4 variables. The question asks us how much heat do you have, and Q is heat, and so I have the other 3, and I can just solve for Q. So I do 2.05 equals Q divided by 150 times 15. And then to solve this, remember, if you know how to solve this, great. If not, remember you're going to multiply those 2 on the bottom first. So 2.05 equals Q over, and then 150 times 15 is 2,250. And then I multiply each side by 2,250. And it's going to be really small, 2,250. Multiplying that. And we get Q equals 4,612.5. However, there still is another step because this is in joules. Remember, and right here we can see C is given in joules. And our answers, your answer choices for this were all in kilojoules. So we need to convert from joules to kilojoules. And remember, kilo means 1,000. And so to convert from joules to kilojoules, I'll do this multiplied by 1 kilojoule. 1 kilojoule, 1,000 is 1,000 joules. You can think of this over 1 if it helps. So the joules cancel. One's on top, one's on the bottom. Then I just multiply across the top, multiply across the bottom. So it turns out to be 4,612.5 divided by 1,000 equals 4.61 kilojoules. And that is your answer for that one. So tricky part about this one, you have to know to find the specific heat in this table. Otherwise, it's just like all the other ones we've done. You just plug in 3 variables, solve for Q, and then the last tricky part is solving or converting joules into kilojoules. Also tricky here, make sure you don't use either of these on the table, right? We're talking about ice. Notice it has different specific heat than liquid water and water vapor, so make sure you're using the one for ice. On this question, your question may be different. You might get a question that talks about water or liquid water or water vapor, so make sure you're reading the question carefully, right? Yours could say something different. It could say any one of these. Just make sure you use the correct specific heat. Okay, next one. Couple more here. What is the change in enthalpy when 250 grams of water vapor condenses at 100 degrees? And that when I copied and pasted these, the degree sign kind of looked funny. This is degrees Celsius, and you get the enthalpy HV. The enthalpy of vaporization is this. Okay, now tricky part here, what you have to realize, it's giving you enthalpy of vaporization, but it's saying the water's condensing. That's the opposite of vaporization. That is key, and that is where a lot of people messed up on these problems. Yes, that's where most of you got the right number, you got the wrong sign. So these are opposite, so the HC, enthalpy of condensation, when things condense, is the opposite sign of the enthalpy of vaporization. And this is where most people went wrong. A lot of people got the right number, but they got the wrong sign because you need to add in this negative sign. Because it's condensing, it's not vaporizing. Now the first step to this, notice this is in kilojoules per mole and we're given something in grams. Whenever that happens, I think most of you realize we need to convert from grams to moles. So we have grams of, I'll write this properly, H2O times 1 mole of H2O equals 18 grams of H2O. So grams cancel. I'm left with moles, multiply across top, multiply across the bottom. So 250 divided by 18 equals 13.89 moles of H2O. And so now I can just do this. So I have my enthalpy of condensation, negative 40.67 kilojoules per mole. So I can just do negative 40.67 kilojoules is on top, right? And moles, this is divided by moles, is on the bottom. So conveniently enough, moles cancel. And we're left with, we just multiply across 13.89 times negative 40.67. Negative 564.86 kilojoules. All right, and the important thing is a lot of people got the right number, like I said, but they did not flip the sign here, because this is the enthalpy of vaporization, HV, and we're going the opposite way, we're condensing. Okay, last one real quick. Oh, I only have about a minute left on the screencast. This diagram would represent the enthalpy changes in which of the following? And you have hot pack, boiling liquid, cold pack, melting solid. The answer is hot pack, because this is an exothermic reaction, right? Reactants have more energy than the products, so the energy is being released as heat normally, and so that's what a hot pack is, right? It feels hot because it is releasing heat. This is an exothermic reaction, and so that's what hot packs are. All right, guys, remember to write down the password coming up here, and good luck on the retake.